Hi everyone! Today we'll be looking at special right triangles, specifically at the 45-45-90 triangle. Here's today's learning target. Given a right triangle with special angles, I will be able to find the lengths of the missing sides. So in this lesson, as well as the next lesson, we'll be looking at special types of right triangles. We've been looking at the Pythagorean theorem for the past few lessons, and the Pythagorean theorem is basically a theorem to help us find the third missing side when given two sides of a right triangle. And the Pythagorean theorem states that a squared plus b squared equals c squared. A and b are the leg lengths, and c is the length of the hypotenuse. Remember that the hypotenuse is always on the opposite side of the right angle. But what if you have only one given side? What can you do in that case? How do you find the missing side lengths? Well, if you have special right triangles, then you only need one side to find the other missing sides. Today, we'll be looking at the 45-45-90 type of special right triangle. So before we get to looking at the actual right triangle, let's do some sketching first. You can just follow along here. So let's say I have a square with the side lengths being a unit of 1. So I have a square here, and since it's a square, I know that the four angles are all right angles, so each angle measures to 90 degrees. Now let's say I split this square in half across this diagonal. Notice that I now have two triangles, and they're both right triangles. Let's focus on this right triangle right here, and let me color it in so that you can see it a little better. So I have a right triangle here, and let's look at the angle measures. So I have a right angle right here, measuring to 90 degrees, and up here, notice that the 90 degrees was split in half by that diagonal line, so it's 45 degrees. Same with the angle down here. And I can make sure by adding up the three angles, and I notice that the three angles do add up to 180 degrees. I'm also going to look at the side lengths of this triangle, so I know that each leg has a side length of 1. But what about the hypotenuse? What's the length right here? Well, I can actually use the Pythagorean theorem. A squared plus b squared equals c squared because we have a right triangle. A and b are both 1, and we're solving for c. Let me know if you have questions on these steps right here. I get 2 equals c squared, take the square root of both sides, and c is the square root of 2. So c equals radical 2, so the hypotenuse length is radical 2. I was able to create a 45-45-90 triangle and find its side lengths. So we were able to find this special right triangle, and the condition for this special right triangle is that the angle measures are 45 degrees, 45 degrees, and 90 degrees. In this case, the legs are the same length. So this side, which is a leg, has a side length of 1, and so does this leg over here, also 1. And the hypotenuse length is 1 times this radical 2. So a 45, 45, 90 triangle is always going to have this kind of side length proportion where it's like a 1 to 1 to a 1 times radical 2 type of ratio. And so that means that if we have a 45, 45, 90 triangle, even if we only know one side length, we can easily find the other two side lengths. So let's go ahead and take a look at some example. So here I have a 45, 45, 90 right triangle. So this is a special right triangle. And I am asked to find the missing side lengths. I'm given the leg length, but I have to find the other leg length as well as the hypotenuse length. I like to color code so that I know which sides are the legs and which side is the hypotenuse. Remember, the hypotenuse is on the opposite side of the right angle. I know that in a 45, 45, 90 triangle, the leg lengths are the same. And we're given that the leg length here is 3, so I know that the other leg is also 3. And the hypotenuse length is also 3, but with that extra radical 2. So in this case, we were given a length of one of the legs, and we were able to find the other two missing side lengths. The legs have the same lengths, and then the hypotenuse is very similar, just with that extra radical 2. Let's look at another example. Here, notice I'm missing an angle, but we'll talk about that. And we're given one of the side lengths. We have to find the other two missing side lengths. Right here, the missing angle is 45 degrees. And I know this because the three interior angles of a triangle must add up to 180 degrees. So here, once again, I have a 45, 45, 90 triangle. Next, let's identify which sides are the legs and which side is the hypotenuse. So we're given one of the leg lengths. Here's another leg. And the hypotenuse is on the opposite side of the right angle. So I know that the missing leg length is 8, and the hypotenuse length is also 8, but with that radical 2. So here, once again, I was given one leg length, and I had to find the length of the other leg, as well as the length of the hypotenuse. And this ratio only works because we have a 45, 45, 90 triangle. For our third example, notice that the triangle is facing a different direction, but we're still going to use the same idea of a 45, 45, 90 triangle. Regardless of which way the triangle is facing, the hypotenuse is always on the opposite side of the right angle. So there's my right angle, and the hypotenuse is on the opposite side. So the length of the missing leg is also 12, and the hypotenuse length is 12, but with that extra radical 2. So this example, just notice how the triangle is facing a different direction, but we still use the same idea of a 45, 45, 90 triangle. Just make sure you're correctly identifying the legs and the hypotenuse. Here is example 4. Notice that we're given one of the side lengths. Just because you see a radical, don't automatically assume that that's a hypotenuse. Still remember to correctly identify the legs and the hypotenuse. So in this case, I'm given that the leg length is the square root of 2, or radical 2, so I can find the other leg. And the hypotenuse is a little different. It's radical 2 times that extra radical 2. Let's simplify this. This is the same as the square root of 2 times 2, which is the square root of 4, which is just 2. So in this case, the hypotenuse length is 2. So this example was a little different just because we had that radical as a leg length, but the idea is still the same. Okay, let's look at example 5. We're going to find the missing side lengths of this 45, 45, 90 triangle. What's different about this example compared to the earlier examples? In this example, we're given the hypotenuse length, which is 5 radical 2, and we have to find the missing lengths of the legs. This is pretty simple. You just look at the hypotenuse and look at this number right before the radical 2. It's 5. So I know that the missing lengths of the legs are simply 5. Here again, we're using that ratio that we looked at the very beginning, where it's kind of like 1 to 1 to 1 times radical 2. And we use that ratio to find the missing leg lengths. Let's look at a similar example, just facing in a different direction. So we're going to find the missing side lengths here. We're given the hypotenuse length, which is 14 radical 2. Again, the hypotenuse is on the opposite side of the right angle. We have to find the missing leg lengths. And here, I just look at what comes right before the radical 2. It's 14. So I know that the leg lengths are 14. So I say this over and over, but I think it's one of the most important steps. Make sure you're correctly identifying the hypotenuse as well as the legs. Here is example 7. We are given the hypotenuse length, this length right here, which is 9. And we have to find the missing lengths of the legs. But I noticed that something's different here. I don't have that extra radical 2 in the hypotenuse length. So I'm going to rewrite it so that it does have that radical 2. So instead of just 9, I'm going to multiply it by radical 2 over radical 2. I'm going to rewrite this one more time by moving over the denominator. So I have 9 over radical 2 times radical 2. So I moved this denominator over and just rewrote it. So now I have the form we're used to where it's something times radical 2. So I know that the leg length is 9 over radical 2. But remember, we want to rationalize the denominator. So instead, we'll write this as 9 radical 2 over 2. And I know that the other leg has the same length, so let's just write that right here. So I've found the 2 missing side lengths. So I know that radicals can definitely be confusing, especially the first round that you look at it. So be sure to pause and re-watch this example and walk through it as many times as you need to. And please let me know if you have any questions on any of the steps. Okay, let's look at our final example for today. We're going to find the missing side lengths. Here I'm given the hypotenuse, which is radical 6, and I have to find the lengths of the legs. So I look at radical 6, and I notice I have to rewrite this because I want that radical 2. So same steps as earlier. and just kind of moving things around, I get radical 6 over radical 2 times that extra radical 2. And from here, I can easily spot the leg length. It's radical 6 over radical 2. Let me write that over here. But I can simplify this. That's the same thing as the radical of 6 over 2. 6 divided by 2 is simply 3. So the missing leg length is radical 3, and it's the same over here. So even when you see radicals or don't see radicals in the hypotenuse, it's still the same idea. You just want to rewrite the hypotenuse length so that it's something times radical 2, just so it's in that 45, 45, 90 ratio format. So today we looked at one type of special right triangles, the 45, 45, 90 triangle. And in a 45, 45, 90 triangle, the sides have the ratio 1 to 1 to 1 times radical 2, with that radical 2 part being the hypotenuse length. Great job today, and please remember to submit your notes on Canvas.